Hi, welcome back to McClutchy Maths. My name is Natalie McClutchy and today I'm going to be talking to you about network flow. Now this is coming towards the end of our unit on networks and graphs and matrices for Year 12 General Maths in Unit 4. Please like and subscribe to the channel and stay tuned for my next video that will follow this one, which looks at minimum cut theorem. Let's get started with some new ideas. We've looked already at some network flow diagrams in different contexts, and today we're talking only about directed graphs, which we also call, if you remember, digraphs. And these use arrows to show flow through different networks. So we're going to be looking at different kinds of networks with some sort of flow on the way through them. So if you think about my previous slide, which had some traffic flowing through a city, we could be looking at water flowing through pipes, electricity flowing through cables, internet download flowing through cables in a computer network. There's all different kinds of networks that we could be considering. So we're looking at the flow through the network of whether it's water, electricity, bandwidth of the internet, or traffic and cars on the road. Our objective is that we want to maximize the flow that takes place through our network. So we want to make sure that what we have coming in to our network, that our network is actually capable of handling that volume of traffic through that network, and that it's able to move right the way through to the end so we can maximize that flow. Now, in these kinds of diagrams, we've looked at some previous diagrams, we've looked at processes and we labeled our edges. In a network flow diagram, we label our vertices. Now, these vertices could represent a number of different things. It could be a town, so we might be considering those edges to be roads traveling between towns. These could be actually like devices in a network like routers or modems, and the edges that are flowing through them could be the cables that is conducting our internet bandwidth between those different devices. These different vertices could represent dams and reservoirs between towns. So they usually represent physical things, and then these, the edges that are running between the vertices also represent physical things like a pipe or a cable or a road or a railway network. Now we've got some new vocabulary to talk about when we're talking about network flow. So we've got something called the source, and this is indicated by our starting vertex, or sometimes more than one vertex, which would be vertices. And some textbooks, as we've mentioned before, call those nodes. Now our source represents the supply of flow to the whole network. So if you've done economics, you would have heard about supply and demand before, and I'm going to talk a little bit about that in a moment. So this is the supply or the source to the whole network. We've also got something called the sink, and this is our final vertex or vertices where all of that flow through the network ultimately ends up. It falls into the sink. So if you can think of maybe water flowing through pipes from the dam, and then it ultimately ends up in our sink and down the drain. Now our sink also represents the demand of the network as well. So all of the people that are within that network, whether they're homes or whether they're devices or whether they're different dams and reservoirs, they have a certain demand on the network that they're requiring a certain amount of flow to come into them. So you may see in some textbooks talking about demand, and that's usually talking about the outflow to the sink. And you may see some textbooks talking about supply, and that's talking, as I said before, about the inflow from the source. You're also going to hear about something called flow capacity in your network. So in one of these types of networks, you're going to have every edge labeled with the maximum amount of flow that it allows through the network. And we're going to do two worked examples in this video, and you'll see how that actually works in the different networks. So the capacity of those edges, whether those edges represent pipes, that might be, for example, 300 liters per second that can flow through that pipe because of the size of that pipe. So we also talk about this flow usually in terms of a rate. So that could be liters per second or megabytes per second if we're talking about an internet network. Or it could even be cars per day or cars per hour, depending on the context. So you're usually going to see that flow represented as a something per something, a rate. That becomes important because when you're presenting answers about the flow capacity of a particular edge or of a whole network, you want to make sure you give your answer with the correct units of measurement. We've also got something called inflow capacity. So the inflow capacity of a particular vertex is the total of all of the flow capacities of all the edges leading into that vertex. So if you look at this particular diagram that you've got below, you've got vertex B, for example. it only has one edge leading into that vertex. So the inflow capacity of B is 1,000, whatever that 1,000 is made up of. So in this case, it's only limited by that one edge that's coming into it. On the other hand, if you look over at the sink on the other end, which is represented by vertex I, it's got three different edges leading into it. It's got the top edge of 50, the middle edge coming from B of 800, and then it's got that bottom edge coming out of H of 200. So the inflow capacity for I is the sum of those three edges. 50 plus 800 plus 200 is 1,050. So you may need to do some fairly simple additions when you're working out inflow capacity. In the same way that inflow capacity is about the capacity of the edges coming in, outflow capacity is about the edges coming out. And sometimes you're going to have an amount coming in and an amount coming out. So now I want you to think in terms of how that would work logistically in real life. For example, in this diagram below, I've got 1,000 coming into vertex B, or I can look at it as the outflow capacity is the 300, 800, and 150. So these are the different edges coming out. They've got a collective capacity of 1,250. Now, if you think about this logically, if only 1,000 can get in, then only 1,000 can come out the other side. There can't be magically more coming out than is actually coming in. So there's a limitation on your outflow, which is whatever that inflow is going to be. So you always take the minimum of the two choices. So in this case, we would say that the outflow capacity from B is 1,000 because you can't get more than 1,000 coming into B in the first place. So then therefore you can't have 1,000 coming out. So if you think about that in the context of maybe a pipe coming into a house, if only 1,000 litres can get into that house per second, you're definitely not going to get a greater outflow than your inflow. Have a look again at this particular example, the outflow capacity from D. Now in the case of D, you've got 800 coming in, but only 400 can go out. So your outflow capacity can only be the smaller of these two amounts. So the outflow capacity of D is going to be 400. Now if the case was reversed where 400 was flowing in and 800 is flowing out like was in that previous example, it's always going to be limited by whatever is smallest. If they were pipes, whatever that pipe, the smallest pipe can handle. We've also got something called residual flow capacity, and other textbooks call that the excess flow capacity. And what that means is the difference between the actual capacity of the pipe or the cable or the road compared to what's actually going through it. So if I look, for example, at vertex H, well, it has a capacity of 200 to come out of H, but only 100 can get into H in the first place. So the difference between the two is 100. So that means that there's this excess capability that H has of 100. So that could be, for example, if it was pipes and we're talking about water, it's got this ability to carry 200 litres per second, but it's only ever going to be carrying half of that, 100 litres per second. So it's got this excess capacity of 100 litres per second. Now remember we said earlier that we wanted to be able to maximise our flow through the network. So these limitations between the inflow and the outflow, maybe you've got too much ability of your inflow coming in, but your pipes coming out or your cables coming out can only handle less than that. So we sometimes have these imbalances in our network, and that creates this residual flow capacity. Now, ideally, for a network to be extremely efficient, you want whatever's coming in to be able to get to the other side. You want supply to be able to meet the demand. Obviously, if you've got a greater amount of supply coming into your network, so for example, we see that coming from our source, we've got 1,000 coming in. Now, if B was not able to take that 1,000, what's going to happen is you're going to have a network that's got all this capability to take all this extra resources, and it's not actually able to use those resources. So the network itself, people, if you were living in that network, you're going to be quite dissatisfied because you know that you've got this capability of 1,000 coming in and you can't use it. On the flip side, if you've got a network that's capable of taking a great deal, for example, you might have your house NBN ready and it's capable of these wonderful internet speeds, but if the source from the node is much slower, like was the case in my house for a long time, you're going to be frustrated because you've got this network that you've spent a lot of money on, you've got all this equipment, and you're going to be unable to use it because the inflow is not going to meet the demands of the whole network. So that's why this whole unit that we're looking at, it's a really good idea to take a step outside the mathematics and have a think about the logic of what's actually going on in the context of these situations. And if you can really picture what's going on and what the implications of what's going on mean, that's going to really help you with those complex, unfamiliar questions in an exam. Okay, so we also look at something called the flow capacity of the whole network, and that's the total flow that's possible through the entire network. And obviously that flow capacity is going to be limited by some of those junctions and intersections where we've got that disparity between the demand and the supply. So for example here, we've got this flow capacity of 950 coming out of here, and this is indicated by these three different conduits into I. We've got 50 plus 800 plus 100, which is the limitation of that bottom set of edges. So the most this network is going to be able to take at the sink is 950, but our source has 1,000. So there's this difference between what can come into the network and what the network can ultimately handle on its way out. So our total flow capacity of that network is 950. Now this is a fairly easy example. I'm going to take you through some more complex ones in a moment. We've also seen in some textbooks that flow capacity has a different name, maximum flow. So it's a really good idea. So as you've seen in this video, there's a couple of different terms that are used interchangeably with other terms. So it's a good idea to be used to seeing the questions in different way and being familiar with when you're asked about the flow capacity of a network that it's also called maximum flow. So when you see these different terminologies and they're different to what you're expecting, that you know what they're talking about. So let's look at our first worked example. This is a fairly straightforward one. You may want to pause for a moment and familiarise yourself with the diagram. So this particular diagram is going to represent the flow of electricity through cables in volts per second. So we're told our units of measurement, so it's going to be very important whenever we're giving answers that we use our units of measurement. We're asked to find the outflow capacity from the source. So thinking about the source, that's vertex S, and we're looking here at all of the different edges that are proceeding out of S. So we've got a edge coming out to A, we've got an edge coming out to B. The edge coming out to A has a capacity of 1,000, the edge coming out to B has a capacity of 1,500, and also the edge coming out to C has a capacity of 500. So we've got three different edges that we need to add together here. They're indicated there with the circles, and so that when we add those up together, we've got 3,000 volts per second. So you could also be asked how much electricity is being supplied to the network from the source. Well, that's the same thing as the outflow capacity from the source. It's 3,000 volts per second. 1b asks for our inflow capacity to the sink. So now we're looking at vertex D. We are looking at the sum of all of the different edges that are coming into D, and these are going to be indicated with the circles. We've got 1,900 coming in from B, we've got 500 coming in from A, and we've got 800 coming in from C. So adding those up together, we get 3,200 volts per second. We're now asked to find the maximum flow into C. So you'll notice that there's two edges coming into C, so we need to add those two edges together. We've got the edge of 500 coming from the source and also the edge of 300 coming from A. So the two of those added together gives us 800 volts per second. So there's nothing particularly difficult about this. You've just got to examine the network and have a look at which way the arrows are pointing to make sure that you don't make any mistakes. The next one wants to look at the outflow, the maximum outflow from C. So coming out of C, I've got 800 going into D and I've got 400 going into B. So the sum of those two outputs is going to be 1,200 volts per second. And example 1e, the maximum flow out of A. So the same sort of thing here, we're going to be adding 300 to 500. These are the two outputs from A. They're circled there on the particular diagram, so that's 800 volts per second. So nothing particularly difficult about this type of question. Let's have a look at a more complicated network. This is my second example today. We're going to talk about maximum flow in this particular one. So we're looking at the big picture of the whole network. So in this particular diagram, we've got an internet network, and I do apologize to anybody who works in internet programming and computers. Hopefully I've got the right terminology because I've come up with this example by myself. So hopefully I'm not going to get slaughtered for using the wrong terms here. But we're talking about data flowing through a network. It's being downloaded through the computer network, and we also call that bandwidth, and that's measured in megabytes per second. Now, if you've got a house that's on the NBN, hopefully yours is in gigabytes per second, but my house is a little bit slower. Now, each vertex represents different devices and routers throughout the network that are receiving data, and each edge represents the capability to download data to the next device. So this is a wired network. We need to determine what's the maximum flow that's going to get through to Z. So you may want to pause this one once again just to get your head around the diagram, because there's arrows going everywhere here, vertices, numbers all over the place. So you've got to work out how much of that data is actually getting downloaded to our sink at Z. So we're just, as we previously talked about, S represents our source, Z represents the sink. And because the flow from sink to A can only provide a download speed of 80 megabytes per second, then the outflow from A to D and C will not be 90. So if you look here, coming out of A, there's a capacity for 40 and also a capacity for 50, depending on where you're going. Different types of cables provide different abilities. So there's a possibility that there could be an outflow of 90, but because 80 is only flowing in, it's never going to be able to deliver that 90 megabytes per second. It's only going to be able to deliver 80. So in this case, we can annotate the diagram to represent the loss capacity. Now, not all textbooks do this, but I did see this in Nelson Q Maths, and I really liked the way that they represented it, so I'm showing that here. So in this case, when we show a 40/50, what that's telling you is that the capacity of the edge is 50, that was the original number, but the actual flow that's going to go through is 40, because 40 plus 40 equals 80. So we're going to map this through the network. We're going to have to actually annotate several edges as we do this, because as you're going to find as we go through this network, not every edge is capable of taking the outflow that the inflow is providing. Okay, let's have a look now at what's going on lower down in our diagram with our flow from B into C and E. So you'll notice that 60 megabytes per second is coming into B. So that means that only 60 megabytes can flow out. You can't make more bandwidth than you've actually got coming in. So you've got 20 going out to C on that edge BC, and the edge of BE has a capability of 100. So you're really going to have 60 going through. So we're going to allow that 20 to funnel through all the way to C, which leaves 40 megabytes per second left over to channel from B to E. Now, I don't know if this is the way internet networks really do work in real life, so please forgive me if I've got this a little bit wrong, but let's just apply that example to the diagram anyway. So now I've annotated down the bottom here the 40 out of 100, indicating that it's got a capacity of 100, but only 40 megabytes per second is going to flow through that particular cable. Okay, so let's continue through our network. Let's see now what's happening at vertex C, because now I've got 60 megabytes flowing into C. I've got 40 coming from A. Remember, the capacity was 50, but only 40 is going to come in. And I've got 20 coming in from B. So that means 60 is coming in altogether. So that means I've got a maximum of 60 megabytes per second that can flow out of C. Now you'll notice that there's 3 different cables coming out of C. One's going to D, one's going to Z, one's going to E. So the actual capacity of those is 40 plus 20 plus 30, which is 90 megabytes per second, but I can only give that part of the network 60. So what I'm going to do here is I'm going to satisfy the capacity to D. I'm going to satisfy the capacity to Z. So they're both going to get their 40 and their 20, but I'm not going to send any downloads through to that cable to E. So it's going to have 0 coming to it because there's nothing more to give. Okay, so now I've annotated that part of the network, and now I need to determine that maximum flow from vertex D. Now vertex D, if you recall, had 80 megabytes per second flowing in. That's coming from A and from C. So that means a maximum of 80 can flow out. It's got a capacity of 100, so we represent that as 80/100. 80 coming in, capacity of 100. And now we need to find out what's happening at vertex E as well. So you're basically tracking from the left-hand side of the network at all those decision points right through the network and assessing at each different vertex what's coming in and therefore what can go out. And then as you make each decision, you move your way along the network. So now we're almost at our sink at Z. So we're looking at what's coming in. We've got 40 coming into E from B. So that means only 40 can flow out. And therefore, we've now got total coming into our sink of 80 megabytes per second from D, 20 from C, and 40 from E. So that means a total of 140 more megabytes per second is coming into our final resting point, which is our sink, Z. So now we've determined the maximum flow of our network. It's 140 megabytes per second. Interestingly, you'll notice that at the very start at our source, we had 140 megabytes per second come in, and that's exactly what's coming out. So you could say that this was a fairly efficient network because the supply of 140 megabytes per second is exactly what was needed at the end at the sink. So the demand matched the supply. Obviously, there were certain devices there who were probably getting a much lower bandwidth than they probably would have desired, but overall, you would say that was probably a fairly efficient network. Now we need to determine the excess flow capacity of DZ. Now you could apply this to any of our other edges where there's a difference between the capacity of the edge and the actual flow through the edge. So remember we talked about that very early on in this particular video, also called residual flow capacity. And it's basically the actual capacity, which is 100, take away that the actual amount that's flowing through it, which was 80. So that means that the residual or the excess flow capacity of DZ is 20 megabytes per second. So all that really means, if you think about this logically, is that you've got this cable connecting D to the sink, and it's got that capacity of 100 megabytes per second. It's basically being underutilized. So it could really be delivering a lot greater flow to the sink than is actually coming through it. So it's while we said that demand match supply, this network is not really as efficient as it could be because there's those limitations at the source at A and B. And all of those different places within the network, we've got this excess capacity that's just not being used. So if we increase the capacity, for example, through to A from the source, or through to B, then we could end up with a far faster and more efficient network overall. Well, that's all we have time for today. I hope you'll join me for my next video. Please like and subscribe and tell your friends about the channel. Have a wonderful day and thanks for joining me.